Swayam Prabha. Digital India. Educated India.
Hello everybody. So, today I am starting the lecture 3 of module 4. I was continuing this discussion of circular plate formulated in polar coordinate system, and in that case we have derived the differential equation of equilibrium involving the r and theta, and then we have seen that if the plate possesses rotational symmetry in respect of support and loading condition, then we can convert the partial differential equation into ordinary differential equation, since the deflection and this load and other stress resultant will not be a function of theta. So, in that case we have seen that equation can be arranged in such a manner that successive integration can yield the desired deflection. So, after the deflection is obtained, then we can calculate the bending moment and shearing force, because in that case the radial moment and tangential or circumferential moment, these two moments are of important in axisymmetric problem, but this m r theta that you call the twisting moment is 0 because of symmetry, and q theta is also 0. Okay. So, now let us show further application of this axisymmetrical formulation by giving more examples in practical cases. So, we will today discuss the bending of solid plate as well as annular plate supported in different manners and carrying the load in symmetrical loading. Under symmetrical loading condition only we can discuss this formulation, because it is a axisymmetric problem. Okay. So, sometimes the plate may not be fully solid, means there may be hole in the plate. So, if the hole is symmetrically placed on the plate, circular plate, then again the problem falls into category of axisymmetrical bending of the circular plate, and in that case we can find the solution of the annular plate, which has various practical applications like this annular raft foundation for circular water tank, the column of a circular water tank which are arranged in a circle, perimeter of a circle, then it can be this type of column can be founded on a annular raft. So, there are other practical applications of the annular plate or plates with hole. So, that will be discussed today's lecture. Okay. So, outlines of the lecture I am now giving you point by point. Solid circular plate subject to concentrated load at the center, annular plate subject to symmetrical edge moment, and annular plate subjected to distributed load. So, three types of problem we will discuss now, and you will see the problem have the different characteristics. In some cases you will find that boundary condition have to be satisfied in the inner region as well as outer region, in especially in case of this annular plate, or in some case you will find that especially for concentrated load that I have given in the first item, there you will find that discontinuity arises at the application of the point of concentrated load in the expression of slope and this curvature. So, that means when the concentrated load is acting just at the below the point of application of the concentrated load, the slope and deflection cannot be found out, but in the vicinity of the load this can be found out in fact, there is no load which is concentrated. Actually, any load has some distributed area. So, practically if such load occurs in the plate, especially the concentrated load at the center, then we can find in the vicinity of the load the bending moment, and then we take the to the right and left of the load, and we can take the average of these two quantity to find the bending moment at the center. Okay. So, let us go to the topic. So, here a plate is shown of circular shape, thickness is h and the radius is a. It is subjected to a concentrated load P. Okay. Now, this plate may be supported in manner say that it may be clamped along the periphery, or it may be simply supported along the periphery, but since it is a axisymmetrical problem, this support condition must be also symmetrical about the rotational axis. Now, here rotational axis is the vertical axis, that is the line of application of the load. Okay. Now, we can solve such type of problem by taking the differential equation of the equilibrium that we develop for axisymmetrical plate, but we can adopt to any of these two equations. One equation is that relating the fourth derivative of deflection to the distributed load, and the second one is relating the shear forces to the externally applied load. So, since there is no distributed load, the second option will be better in this case, because in absence of distributed load, the forcing function of the differential equation cannot be written here. So, let us go to this equation, that the second equation which relates the deflection with this third derivative of deflection with the shear force, that can be taken here with convenience. But another form is also existing, this relating the fourth derivative of the deflection to the distributed load, but this form cannot be used here because of concentrated load action. Okay. So, what we do actually, we take a slice of the plate at a radial distance r and consider the equilibrium of this slice. So, this slice is considered here, and equilibrium of vertical forces, especially to relate the shear force to the externally applied load, we will consider the equilibrium of the vertical forces. So, free body diagram showing the vertical forces are shown here in this figure, and now we can write the differential equation of the plate relating the third derivative of the deflection to the shear force per unit length. So, the equilibrium equation now takes the form d by dr bracket 1 by r d by dr first bracket r dw by dr bracket first bracket closed and third bracket closed equal to minus qr by d. So, this equation you can see this quantity is the slope dw by dr, and then it is differentiation is taken 2 times to obtain the third derivative and to relate this to the shear load, shearing force. Now, observing the vertical force equilibrium of the slice in figure 2 okay, or figure 3 whatever you call, then we can write that any radial distance the total vertical shear, that is q r multiplied by the length of the slice. Okay. Now, the slice is also a circular in shape. So, the perimeter will be 2 pi r. So, q r into 2 pi r is the total shear force. This must be balanced, or the sum of the all vertical forces should be equal to 0. So, if I take the shearing force direction in the same direction of the load, then we can write this with a positive sign and equate to 0. From this equation 2, we get q r equal to minus p divided by 2 pi r. Okay. So, this is the equation for shearing forces per unit length subjected to a concentrated load at the center at a radial distance r. So, now we can QR can be substituted in the equation 1, and then we can get the differential equation relating the concentrated load with the third derivative. Okay. Now, in order to do this, I write this substitute this QR with this minus P divided by 2 pi r. So, this equation now becomes this this d by dr, third bracket 1 by r, d by dr, first bracket r, dw by dr, first bracket closed, third bracket closed, equal to P by 2 pi r d. So, this equation is actually the shearing force equation, and that has to be integrated to extract the deflected surface W. Okay. Now, the steps are underlined. So, integrating equation 3. So, if I integrate the equation 3, then I get the expression inside the third bracket directly. So, I get 1 by r d by dr, first bracket r dw by dr, and in the right hand side I will get, because P by 2 pi d is a constant. So, P by 2 pi d is a constant, I can write here, but 1 by r integration will be log r. So, P log r is given in the numerator. So, P log r divided by 2 pi d, and then constant of integration appears, and we name it as C1. Okay. Now, you can see that log r term is coming because of reciprocal of r, that is appearing in the equation 3, and when we integrated dr by r, the log r terms appear. But mind that this log r has to be evaluated with respect to the base e. So, this is a natural logarithm that we have to evaluate. Okay. Now, let us proceed, go ahead. So, what we will do here, again you see we have to integrate, but before integration you are seeing that 1 by r term is associated in the left hand side. So, if I integrate this equation, then parts by integration by parts will give you a complicated expression, and you will not be able to get this W so easily. So, what can I do? I eliminate 1 by r, that means I multiply both sides by r, then the right hand side there will be no differential coefficient involved. So, whatever the order of r or degree of r appears in the right hand side, it will not give trouble for integration. So, multiplying both sides by r, we now write d by dr, r dw by dr, and P r log r 2 pi d divided by 2 pi d plus C1 r, that is just after multiplying r with r we get this expression, equation number 5. Okay. Now, you can see I have marked it with red color r log r, because this appears as a product of two functions of r. That means, when again I integrate, I require to integrate this expression r log r with respect to r using the integration by parts rule. Okay. So, next, integration of r log dr can be performed by the rule of integration by parts. Now, you have to note here very clearly that when I integrate this r log r, then log r has to be taken as the first function and r has to be taken as the second function. So, after integrating, we get in the right hand side that r log r integration is equal to r square by 2 log r minus r square by r. So, this is the integration of r log r dr. So, hence equation 5 after integration becomes this r dw by dr equal to P by 2 pi d, and this result I substituted here. So, r square by 2 log r minus r square by 4 plus C1 r was there, C1 r. So, integration will be C1 r square by 2 plus C2, another constant of integration. Okay. Now, here we are integrating a third order equation. So, naturally 3 constants of integration will appear. Now, we are reaching our target, that means we have to obtain now the W, the deflected surface. So, the one more step is required. So, divide equation 7 by r. So, we have done this, so that we get sole expression of dw by dr, that after this final integration we will be able to get W. So, dividing this both sides by r, we get in the left hand side dW by dr, that is the slope of the plate, equal to p by 2 pi d bracket r by 2 log r minus divided by r by 4 plus C 1 r by 2 plus C 2 by r. Now, this expression represents the slope along any radial distance, because it is axisymmetrical problem. So, at any angular direction it will be same. Now, you can see the features of this expression. At the point of application of the load, that is load is applied at the center, because it is a concentrated load. So, at r is equal to 0, you will get that dW dr is undefined quantity. So, that means in the vicinity of center only the slope can be evaluated, but not exactly at the center. This is because of concentrated load acting at a single point. In fact, there is no such load acting at a single point. Load has some distributed area, okay, whatever small may be. So, finally, integrate equation 8. So, after final integration, again you see inside the first bracket r log r term appears. So, this expression can be used again here for integration. So, after final integration, we get W r, that is W r is a W is a function of r, deflected surface is a function of r, because it is a axisymmetrical problem. So, there will be no variable theta in the deflection expression, because at any orientation in the plate, the deflection value will be same along the radial direction. Okay. So, p by 2 pi d half r square by 2 log r minus r square by 4 bracket closed minus r square by 8 second bracket closed plus C 1 by 4 r square plus C 2 log r, because C 2 by r term is there. So, after integration it becomes C 2 log r and the final constant is C 3. Okay. After this step, no more integration is required, because we obtained W r, that is the deflected surface, but still some tasks are remaining. So, what happens here, you can see that there are terms which contains P, that is the load. There are terms which contains r square log r. There are terms which contains only r square, and there is also term which contains only log r and only a constant. So, the constant can be arranged or clubbed together, and we can write that W r equal to A r square, that is r square term. We have isolated all r square term, that is here one r square term is there, that this constant is named as A. So, A r square. Okay. Then only the sole constant, that C 3 we have taken here and named as B, fresh we have named fresh as B. Then the term with P. So, this term is very important, because the deflection, bending moment, whatever we get is due to load P only. If P does not exist in the expression, then there is no value of this solution. Okay. So, here we get this term with P as P 8 pi d, you can see the product of this r square log r, and other terms we have just clubbed together with a constant B. Suppose P 2 pi d r square by 4, that constant term is there with r square. So, it is plugged together with the constant A. So, final expression for deflection now can be written A r square plus B plus P by 8 pi d r square log r plus C 2 log r. So, constant of integration are A, B and C 2, that have to be evaluated applying the boundary condition at the edges. Now, you can examine the expression, nature of the expression. You will be interested, because at the point of application of the load, we will get the maximum deflection as well as we will get the maximum bending moment, it is obvious. But see the expression, if you put r is equal to 0, then deflection is not finite here, okay, because this term is becoming unbounded and this is r square log r. So, 0 multiplied by any high number will be 0. So, this term will give trouble in the expression. So, therefore, for finite deflection we drop the constant C 2 and therefore, final expression for the deflection can be written as W r equal to A r square plus B plus P by 8 pi d r square log r. So, this is the final expression for the deflection. Okay. Now, with this expression that is evaluated for a concentrated load acting at the center, we can now proceed to evaluate the value of deflection, bending moment, etc., based on the boundary condition. Okay. Now, first let us consider a clamp boundary, that is plate is clamped at the periphery, a circular plate clamped or welded, a plate is welded at the periphery, or say for example, a circular slab in a assembly hall or somewhere in a temple, it is supported on a ring beam. So, this type of application is there and it is subjected to a concentrated load. There may be concentrated load or a load which is distributed over a very small area. So, in that case let us find out the maximum deflection, bending moment, etc. So, at r is equal to a, the edge is clamped. So, the limit of the plate is from 0 to a, the a is the radius of the plate. See this figure, and here therefore, we get the deflection at the boundary is 0 and slope at the boundary is 0 along the radial direction because of the clamp condition. Now, applying the first condition in equation 10.1, what is 10.1? Let us see this 10.1. If I put r is equal to a, then W a equal to 0. So, a small a square plus b p by 8 pi d a square log a equal to 0. So, this we get here a square plus b plus p a square 8 pi d log a. So, this is the first equation for finding the constant of integration a and b. Second equation has to be obtained by applying the condition on slope. At the clamped end, the slope along the radial direction is 0. So, the first derivative of w is 0. So, we have to take the first derivative of w. Since the expression for w is now known in terms of constant. So, we can obtain the first derivative of w. You can obtain this, the first term derivative with respect to r will be twice a r, derivative of b will be 0 because it is a constant, derivative of third term, that p by 8 pi d will be constant term, and here product of two terms are there. So, therefore, you have to differentiate r square first and coefficient will be remaining as log r, plus you differentiate log r and with that multiplication of r square will be there. So, using this we obtain the first derivative of this expression as 2 a r plus p by 8 pi d 2 r log r plus r. So, you can see here this expression is the result of the differentiation of r square log r. So, after differentiation of r square log r, it has decomposed into two terms. Okay. Now, since the slope is 0 at the clamp boundary, r is equal to a, now we apply the clamp boundary condition. Clamp boundary condition is 2 a plus p by 8 pi d 2 a log a plus a equal to 0. This is the condition. So, now we get two equations. One is this equation relating a and b here, and here also another equation, but here b term does not appear because b is a constant which appearing as a sole term, and when we differentiate it, it vanishes. So, in this expression we get 2 a plus p by 8 pi d bracket 2 a log a plus a equal to 0. Okay. From this expression one can see that the constant capital A can be obtained as minus, I take this term in the right hand side. So, it becomes minus p p by 16 pi d. You can see 2 is brought here. So, 8 into 2 16 pi d bracket 2 log a, because it is divided by a. So, 2 log a and it is a by a is 1. So, we get the quantity or constant a as minus p 16 pi d bracket 2 log a plus 1. Now, if I substitute the equation 13, this equation 13 in equation 11 is this, because equation 13 gives the value of a, it gives the value of a in terms of known parameters, because p is known, the flexural rigidity of the plate d, which depends on the material constant E, then mu, and also the thickness of the plate is known, radius of the plate is known. So, the constant A is fully evaluated. So, after knowing the constant A, we can find the constant B from the expression 11. So, A is substituted from the previous equation here, and we can now evaluate B. After evaluating B, this B expression comes as B is equal to p a square plus 16 pi d. So, we get the desired constants of integration that is required to fully know, completely know the deflected surface. Okay. Now, substituting A and B in the deflected surface that we have found from the solution of the differential equation, that is 10.1, we will find that deflection equation now becomes W r equal to p r square 8 pi d log r minus p r square. This becomes this W r equal to p r square by 8 pi d log r minus p r square 16 pi d into 2 log a plus 1 plus the constant term. Okay. So, bending moment expression becomes the minus d second derivative of W plus mu by r, mu is the Poisson ratio d W by d r. Now, after differentiating the W 2 times, and then we can get the slope as well as the bending moment. So, bending moment expression is now written as minus p by 8 pi 2 plus log r square by a square plus mu into log r square by a square. You can see the expression for radial moment. Examine the expression for radial moment. The radial moment at the center does not exist, because the slope is discontinuous, the first derivative is discontinuous, as shown the second derivative also. So, therefore, you have to find this the radial moment in the vicinity of the application of the load, but at the edges the clamped bending moment, that is fixed end bending moment, can be evaluated. So, by putting A in the expression, we can get the maximum bending moment. So, when we put this r square by a square, r is substituted as a. So, this becomes 1. So, log 1 is 0. Similarly, this is also becoming 1. So, therefore, the maximum radial moment that is occurring at the clamped edge is equal to minus p by 4 pi. So, this is the value of maximum radial bending moment, and you can see that this quantity does not depend on the Poisson ratio. Now, let us come to the circumferential moment. Okay. The circumferential bending moment can be obtained by this expression minus d mu into d square W by d r square plus 1 by r d W by d r. Okay. Now, again substituting the second derivative and first derivative of the deflected surface, we get that m theta equal to minus p by 8 pi bracket 2 mu plus log r square by s square bracket closed v mu plus 1 second bracket closed and the first bracket closed. Okay. Now, here you can see this expression m theta is not only dependent on the value of the load and the ratio of the r by a, but also it depends on the material property mu specially. So, at r is equal to a, again this term becomes 0, because log 1 is 0. So, we get at the edges the tangential moment is m theta equal to minus mu into p 4 pi. Now, compared to the earlier value of the moment minus p by 4 pi, if you calculate this value, then you will find this moment is reduced because of this Poisson ratio effect. Then one can find also the shearing force, but shearing force can be found from the equilibrium in the vertical direction or from the calculation finding the third derivative and equating to the shearing force. Okay. Because we know this deflected surface, so we can now obtain the derivative up to third order easily. Let us come to a case where the plate has a hole at the center. So, as I told you, this type of plate is encountered in practical application in several occasions. For example, a circular shaped water tank, elevated water tank is to be constructed, and then we arrange the column in this circumference of the circle. So, for this column which are arranged in the circumference of the circle, it will be convenient to adopt a annular rough foundation accommodating all the column. So, this type of problem is found application in practice, and plate theory for finding this stress resultant can be used. Okay. Now, here we are examining a case where the annular plate is subjected to a moment at the edges. So, at the outer edge the moment is m 2, at the inner edge moment is m 1, and you can see here that the inner edge has a radius of b, that means the radius of the hole is b and outer radius is a. So, total radius of the complete plate is a, but there is a hole at the center, concentric hole, the radius of the hole is b. Okay. So, let us solve this problem. Now, you can see that in the region B r ranging from B to A, that is in this region, okay, there is no distributed load. So, that means shearing force will be 0. So, based on that we can write this equation d by dr 1 by r d by dr bracket r dw by dr bracket closed equal to 0. So, this is the equation or expression for shear force, and this is equal to 0 because no shearing action is taken place here because no load is there. Okay. So, this indicates that the homogeneous equation has to be solved to find the deflected surface. Okay. Now, integrate this equation. After integration, we get the quantity inside this third bracket, and the quantity is 1 by r d by dr bracket closed r dw by dr equal to C 1. So, because this is 0, so after integration a constant term will appear. Now, multiply equation 25 by r. If I multiply equation 25 by r, then it becomes d by dr r dw by dr equal to C 1 by r. This expression can be again integrated. So, after integrating this expression, we get r dw by dr equal to half C 1 r square plus C 2. Then, to obtain w, again the tricks have to be applied, that we now divide this both sides of the equation with r. So, dividing both sides of the equation by r, we get dw by dr equal to half C 1 r plus C 2 by r. Now, integrate equation 28. After integrating equation 28, we now finally arrive at the desired expression of w. So, w is now equal to C 1 by 4 r square, because integration of r with respect to dr will be r square by 2. So, naturally 1 by 4 term factor is coming here, and this term will be C 2 log r plus C 3. Okay. Now, here we are getting 3 constants of integration as expected after final integration, and now the 3 constants of integration have to be found out applying the boundary condition at the edges. Okay. Let us consider the edges are supported, simply supported. Okay. So, that means at this outer edge a moment m 2 is applied and the inner edge m 1 is applied. and in the region 0 to B there is no material, that is a hollow portion of the plate. So, therefore, at r is equal to 0 there is no question of any stress resultant or deflection, because no material is there. So, this expression W r equal to C 1 by 4 r square plus C 2 log r plus C 3 is valid only for the region r in between B to A. So, only in this region it is valid. So, we can keep now all the terms. So, C 1 by 4 r square plus C 2 log r plus C 3, all the terms now are important to find out the boundary conditions of the to find out the deflection of the plate. Okay. Now, at the boundaries we examine that the radial moment m 1 at r is equal to b. Okay. So, at the inner edge the moment that is applied is b, and it is a symmetrically applied moment, edge moment uniform along the periphery, inner periphery and outer periphery. So, that you have to, it is bending under the symmetrical moment, because if the moments are antisymmetrical then axisymmetrical condition, the differential equation cannot be used. So, m 1 is existing at the inner edge. So, therefore, at r is equal to b we now equate the bending moment m r to m 1. Okay. The expression for m r is minus d bracket the curvature, that is the second derivative of w with respect to r, and then plus mu by r, mu is the Poisson ratio, and slope, that is d w by d r. Okay. Now, if you look at this expression, that has to be differentiated. First derivative and second derivative both have to be found out. Now, here you can see after differentiation and applying the condition at r is equal to b and r is equal to a, that is the inner edge and outer edge, we get two equations. The first equation is after application of the condition of radial moment at the inner edge at r is equal to b, we get d bracket C 1 by 2 1 plus mu minus C 2 by b square 1 minus nu bracket closed equal to m 1. And then after applying the boundary condition at the outer edge, that is r is equal to a, we get d bracket C 1 by 2 1 plus mu minus C 2 by a square into 1 minus mu bracket closed equal to m 2. So, two equations now we get, and two equations can be solved for C 1 and C 2, and after solving C 1 and C 2 we go for finding the constant, another constant C 2, but application of two boundary condition gives only the two equations. You see there are three constants of integration, but we get only two equations. So, let us see how the third constant can be evaluated. First, let us obtain the two constants of integration C 1 and C 2. Solving C 1 and C 2 from equation 30 and 31, that can be solved because this is a linear equation with C 2, C 1 and C 2. So, it can be solved by Cramer's rule or by simply this any method you apply from algebra, you can get the value of C 1 and C 2. Okay. So, obtaining the value of C 1 and C 2, we can write now C 1 equal to 2 multiplied by a square m 2 minus b square m 1 divided by 1 plus mu d bracket a square minus b square. Then C 2 is equal to a square by b square m 2 into m 2 minus m 1 bracket closed divided by 1 minus mu into d by into a square by b square. So, these two constants are obtained where a is the outer radius and b is the inner radius, as you have seen in this figure, and m 1 is the inner moment and m 2 is the outer moment. So, that has been shown in the figure. So, other constant C 3 is found from the fact that in the simply supported condition at the edges, say at outer edge the plate is simply supported. So, at r is equal to a, deflection must be 0. So, based on that we get another equation. So, substituting r is equal to a here in this expression, we get C 1 by 4 a square plus C 2 log a plus C 3 equal to 0. Okay. So, this equation we get. Now, combining this term, that is C 3 is equal to minus C 1 by 4 r square plus C 2 log r by a. So, these two terms we have got now, two terms C 1 and C 2 already calculated. So, now substituting C 1 and C 2, you can now get C 3. So, C 3 is calculated as this, C 3 is equal to minus s square by 2 into s square m 2, m 2 is the bending moment at the outer edge, minus b square m 1 divided by 1 plus mu into d into s square minus b square. So, 3 constants of integration is now completely known, because we require only 3 constants C 1, C 2, C 3. 3 constants are appearing because we have integrated a third order equation. Instead of fourth order equation, we have integrated the third order equation. So, 3 constants are appearing. Now, 3 constants here are completely known. So, we can write the expression for deflection as this. Okay. Now, when m 2 is equal to 0, for example, here there is no moment at the outer edge, only the inner edge moment is acting. So, put m 2 equal to 0 in the expression, this expression, and then we can get the expression for W r as this. Okay. Now, let us see how the deflected surface varies with r by a ratio. So, the range of r is from b to a, b is the inner radius and a is the outer radius. So, we have taken the inner radius as 1/4 of the for example, to illustrate the solution, we have taken the inner radius as the 1/4 of the outer radius, and we have taken it is a steel plate whose Poisson ratio is 0.3. The variation of W r with r by a is shown in this figure 6, and 0 is the center, this is the center and this is the outer radius. So, this variation of deflection with r by a ratio for simply supported circular annular plate subjected to edge moment is shown only for this edge moment m 1. Now, you can see here that at the simply supported edge the deflection is 0, obviously as expected, and at the it is not going at the center, because center there is no material. So, at 0.25, because r is equal to only 0.25 a, because we have taken r is equal to a by 4. So, you can see that at r by a by 4, that is at the inner edge, because this is free, the maximum deflection is occurring here. Okay. So, in such a manner we can find the expression for the annular plate. Now, here another variety of problem I am discussing. This problem will be slightly complicated, because the loading is not continuous, because there is a break in the load, although it is axisymmetrical, but there is the load is not containing the full plate. This is also a plate with hole, the radius of the hole is b, but the loading portion is from C to A, that is C is the radial distance from where the uniform load starts and it ends at the outer edge A. The hole with a radius b in the plate exists. Okay. Now, here we have to obtain the solution in two cases, that means first we have to get the solution for inner region and then we have to get the solution for outer region. Inner region I am calling that region where there is no load acting, and the outer region I am calling this portion where the load is acting. So, inner part is say B to C where no load is acting, and outer part is from C to A. Okay. Now, if I see the vertical force equilibrium in the outer part, we can see that total shearing force at any slice will be 2 pi r q r equal to total vertical load acting on the slice. So, total vertical load acting on the slice will be the area will be pi r square minus c square, and q is the load acting on the slice. So, this is the total external load that is acting on the slice should be equal to the total shearing force. So, from that condition we can get q r equal to q by 2 r bracket r square minus c square. Okay. Then we should find the deflected surface by integration procedure, and we adopt the third order equation where shear force is related to the third derivative of the deflection. Okay. Now, here if you solve this by substituting q r that we have obtained here, we can get a solution W. Now, this solution contains 3 constants for the outer region. Okay. Then the inner region also will get a solution. Inner region actually no this force is acting. So, naturally this right hand side will be 0, but we get 3 constants of integration. So, 3 plus 3 6 constants of integration have to be known by applying the boundary condition. So, boundary condition we require 6 in numbers to be applied for to know all the constants of integration, and then we can finally know the deflected surface. For the inner part, if you see that r is equal to b, no moment is acting because it is a free end and no externally applied as moment is there. So, therefore, we take m r is equal to 0 at r is equal to b. So, this is one condition. Then for outer region or outer solution, if you call that we have obtained where the load is considered q. Second condition is at simply supported n, that is the radial moment is 0, m r is 0, that is second condition. Then deflection is 0 at the simply supported n, that is another condition. So, we get 3 conditions to be imposed on the 2 differential equations involving 6 constants of integration. Then another 3 constants are found at r is equal to c, that is this point. Deflection found from the inner part should match with the deflection found from the outer part for satisfying the compatibility of deflection. So, compatibility of deflection has to be satisfied at the common point. So, at r is equal to c, W inner equal to W outer. Then fifth condition is the slope compatibility has to be satisfied at the common point. So, at r is equal to c, again dW by dr inner equal to dW by dr outer. That means, outer and inner solution differentiation has to be taken, it has to be equated. Last boundary condition is the bending moment m r, that is the radial bending moment at this common point on the inner part should be equal to the radial bending moment at this point from the outer solution. So, in this way we get the 6 solutions, 6 boundary conditions, and applying 6 boundary conditions, 6 constants of integration can be evaluated. Okay. Now, lastly I want to discuss a problem of finding the deflection and bending moment in a circular plate carrying concentrated load at the center, whose boundary condition is simply supported. So, that type of problem is also occurring in practice, that is the simply supported edges, and let us see how to solve such problem. Okay. So, we have here this problem of simply supported plate, circular plate. That means, we have a plate which is simply supported at the edges and carrying a concentrated load at the center. That means, if you see a section and at the center there is a load. Okay. So, let us solve the problem of finding the deflection. Okay. The equation of the plate deflection is known we can take the third order equation, we can take the fourth order equation. Okay. Now, here we shall take a slice around the load and consider the equilibrium of the slice. Okay. So, load is acting here P, and we have the shearing force that is acting around the slice of magnitude q r per unit length. Now, from vertical force equilibrium, that is summation of forces in z direction is 0, z direction is the vertical, this is the z direction, and direction of w is also. So, taking the equilibrium of forces, summation of forces in the z direction to be 0, we now get 2 pi r q r, because we take this slice at a distance of r, okay, equal to this p. Both are taken this downward, so it will be minus. So, q r is now equal to p by 2 pi r with a minus sign. Okay. So, this is the q r. Now, let us write the equations of equilibrium, differential equations. So, differential equation okay. Let us write like this: d by dr 1 by r d by dr r dw by dr minus q r by d. Instead of q r, now I put this term. So, this term is brought here, and now differential equation can be written is p by 2 pi r d. Okay. So, instead of p q r, we have now written minus p by 2 pi r. So, this equation now becomes d by dr 1 by r d by dr r dw by dr equal to p by 2 pi r d. Okay. So, after obtaining this, we now go to finding the constants of integration. That means, the equation can be rearranged in this form, final form, and then we apply the boundary condition. So, boundary conditions are at r is equal to say a radius a, r is equal to a, at the boundary, the deflection is 0 because it is simply supported, as well as m r equal to 0. There is the radial moment equal to 0. So, first condition gives this a square plus b plus p by 8 pi d a square log a equal to 0. So, this is one equation after applying the boundary condition. Second equation is obtained applying the radial moment condition to be 0 at the edges. Okay. Now, if I go in the finding the radial moment, then we should know the first derivative and second derivative, because the radial moment contains the curvature as well as the slope also in axisymmetrical in polar coordinate system. So, dw by dr is now equal to twice a r plus p by 8 pi d 2 r log r plus r. Okay. And second derivative of this d square w by dr square equal to twice a plus p by 8 pi d. You see, this is the product of two functions. So, we are differentiating, and after differentiating we are getting say here 2 into say we are getting first say log r, then we are getting 1 plus 1 another term is there. So, final expression is second derivative is twice a plus p by 8 pi d equal to into 3 plus 2 log r. Now, apply the condition of bending moment. So, m r at r is equal to a to be 0. What is MR? MR is equal to minus d square w dr square plus mu by r dw by dr should be equal to 0 at r is equal to a. So, after substituting this value, this d square w by dr square and dw by dr with r substituted as a, we now finally get an expression of a. So, from that condition we get directly the expression for a as minus p by 8 into 2 pi d, because 2 is there in the coefficient of this a. So, we will get in the denominator this term factor 2 into 3 plus mu 1 plus mu plus 2 log a. So, this expression results after simplification. So, ultimately the value of a is now equal to p by 16 pi d 3 plus mu 1 plus mu plus 2 log a. Okay. Substituting a in the expression for deflection that we have previously found at boundary, which is equated to 0, we now get the quantity b. So, b is from our deflected surface equation, that b is minus a square, that is at the boundary, p by 8 pi d a square log a. That means, deflection is equated to 0 at the boundary and we get this expression. So, this expression is evaluated finally after substituting a here. So, after substituting a, we get after simplification b as p a square by 16 pi d 3 plus mu 1 plus mu. Okay. So, a and b, two constants are known for this simply supported plate. Okay. Let us find this deflected surface. So, once the a and b is known, then we can write a r square plus b plus this expression the containing the load that has to come here. So, p r square by 8 pi d log r. After substituting the value of this a and b, we now finally obtain the deflection in this form, that is deflection will be now written or simplified as w r equal to p a square by 16 pi d 3 plus mu 1 plus mu 1 minus r square by a square plus p r square 8 pi d into log r by a. So, this is the expression for deflection. Now, you can see the maximum deflection occurs at the center. Occurs at the center and it is natural, because this at the center the load is applied, concentrated load at r is equal to 0. So, putting r is equal to 0 here, you will get the maximum deflection. So, W max equal to p a square 16 pi d 3 plus mu 1 plus mu. This is the maximum deflection. Now, if I want to find the second derivative of this expression and first derivative of expression, then wanted to calculate the bending moment, we can now find the bending moment also. So, the bending moment m r can be found minus d square w dr square mu by r dw by dr. Okay. So, you can see the maximum deflection occurs at the center, but when you find the derivative second derivative and substitute this in this expression, you will be noticing that at r is equal to 0, the bending moment does not exist, because of the discontinuity of the slope and curvature expression. So, because of the concentrated load at the center, the slope and derivative exactly at the center r is equal to 0 does not exist, but we have to find the slope and curvature in the vicinity of the center, that 0 plus epsilon or 0 minus epsilon, and then we can take epsilon is a small quantity, and then we can take the average of these two values to get the bending moment. So, axisymmetrical problem I have fully discussed now, and I hope that you can now proceed to tackle the problem of circular plate subjected to axisymmetrical condition, that is on the boundary and also with respect to load. Okay. Two formulations are necessary, one is the shear equation and another is deflection equation, that is relating the fourth order of derivative to the load. Any of these two equations you can apply depending on the conditions of the problem. Okay, thank you.